Now we come back to the more general situation. So we have an array of n variables, and we have this binary decomposition that for every ij, we state that xi must be different from xj. Okay? And so this is this situation. And the filtering that you will get with this binary decomposition is the filtering that we call the forward checking filtering for the all different constraints. And let's consider what happens when one variable becomes bound. It needs to be removed from the domains of the other variables that are involved in the all different constraint. So how much time does it take to filter this decomposition? Assume now that x2 is bound to 2. Okay, this is this variable. x2 becomes bound. Then we need to remove 2 from the domains of all the other variables. Okay, we need to scan all the other variables where this variable was registered. To filter a new event such as one variable becomes bound, for the forward checking filtering, we would need to scan all the other variables. So it means that we would take theta of n just because one single variable is bound. Okay, so we will pay a cost that is proportional to the number of. The idea is that we would like to, instead of having to pay a cost of n, we would like to pay a cost that is proportional to the number of unbound variables. So ideally, we would like to only pay a cost that is proportional to here the fact that there are only 2 variables or the variables that are not yet bound when x2 becomes bound. Okay? So this is what we would like to have. Of course, this is exactly the optimization by deactivating the constraint before that I just explained that we could get. But we would like to implement that in one single constraint, okay, so that it's much more efficient than having to post a quadratic number of constraints. We would like to have one global, all different constraint that would take care of all the n variables at once, okay? And we would like to pay a cost proportional to the number of unbound variables. So how do we do that? We already met a similar issue with, if you remember, with the sum constraint. For the sum constraint, we also had this idea of paying a cost that is proportional to n for every variables. And then we had this idea that using sparse sets, we could only take care of the unbound variables as well. Okay, and so this was the idea of speeding up a little bit the reasoning, the filtering for the sum constraint. We will use the same reasoning here and the same modeling trick. So why, just to a little bit tell you why is it important to do this, is because you should never forget that most of the time you spend it at the bottom of the search tree, right? This is really the huge part of the search tree is at the bottom, okay? And at the bottom of the search tree, most of the variables are bound. So just to give one number, let's say that you have 100 variables. Maybe here at the bottom of the you have 3 or 4 variables that are not yet bound. Okay, so you have a very limited number of variables that are not yet bound, and unfortunately, this is where you spend most of the time in the search. And so the idea is that, and I give the number here actually. So for the 15 queens problem, so you have 15 variables on average, when the all different constraint is called, when the propagator is called, you have more or less 11 variables that are already bound. So it means more or less 4 variables are not yet bound. Okay, so it's quite important to avoid to scan these 11 variables that you already know that they are bound, because you have nothing to prune there anymore. And so you can really speed up the pruning by not considering them. So how to do that, as I said just a little bit a while ago, is we can use the same idea as for the sum constraint. We will use a sparse set to split the variables, the index of the variables between the ones that correspond to the bound variables and not yet bound. And so we will use here a reversible integer, a state integer, to remember the number of unbound variables. Okay, so this is this one. And then we will scan them. Okay, so we have the n variables here. Okay, 1, 2, okay. We will scan them from right to left. And as soon as we see that one variable is bound, we will swap it. We swap it with the last one, okay, and then we decrease the number of unbound variables. Okay, so we swap and then we decrease this number. This is what we do here. You see that we are scanning. I will remove it. We are scanning from the right to the left. If you realize that the variable y is bound, okay, at indexes, we will swap the two indices, and then we decrease this number of unbound variables. And then, of course, at the end, we update and we set the value of this state integer so that it can recover its value on backtrack. Okay, so that's the sparse set ID. We can reuse this same ID. And the benefits of doing that is that then for the all different constraints, we only have, when we realize that one new variable is bound, we only have to scan the unbound variables to consider the removal of these new bound values in the all different constraint. So what do we gain? I did a small experiment just to show you what we gain with this. If I use the forward, so that's for the 15 queens problem, and I decided to scan all the solutions. So I'm looking for all the solutions. You see that there are a huge number of nodes to explore. The search tree is quite large. With the forward checking algorithm using the sparse set, the time required is 43 seconds to explore my laptop. And with the binary decomposition without the sparse set, you see that it's 63. So just with this little optimization, you see that we can gain something like 53% of time just by using this sparse set ID. Okay? Okay, let's increase the number of variables. And now we have, instead of 15 queens, we have 30 queens. And we are looking for the first millions of solutions. In that case, it would be very time-consuming to scan all the solutions. This is why I stop at the first million solutions. With the forward checking, 36 seconds, okay, and with the binary decomposition, so this was the one with the sparse set, you see that it's 69 seconds, and so the gain is even larger. So when you increase the number of solutions, the number of variables, you see that the speed up is larger and larger. And so for very large problems where you have a large number of variables, not 15, but maybe hundreds of variables, you can really have substantial gains by using this sparse set ID to speed up the filtering, the forward checking filtering of the all different constraints. So again, we don't have more filtering than with the decomposition, but by considering it globally and by splitting the set of variables between the bound variables and the unbound variables to make it more incremental and having to scan all the n variables every time the propagate method is called, you see that the speed up is larger and larger with a larger number of variables. Okay, and this was expected, of course. In the next video, I will consider the efficiency in terms of filtering, the number of variables that we are able to remove for the constraint.